right, so we're going to start with section 4.2, and we are going to actually figure out how we create the least squares regression line. And then we're going to use that to make predictions. After we do create our line, we can talk about what the slope and y-intercept of those lines mean for their scenarios. So just like before, I'll show you kind of how we do this by hand, and then how we can do it with technology. So to get started here, we're going to go back to that club head speed and distance that the ball traveled that we looked at in the last example, or the last, it was the kind of the last example, but the last section. So the first thing we're going to talk about here is how we create our linear regression equation. So if we didn't have any access to technology and we just want to kind of guess, this would be where we would start. So I'm going to kind of start with the whole guessing process and eventually lead us to how do we really get the best equation? Because if we're just guessing, we could each work with different pairs of points. Because the first thing you would do is, if you were creating your own linear regression, is you would pick 2 points that you think you could draw the best line through. So what they do here is they chose these 2 points, 99 to 58 and 105 to 75. Because a line drawn through these 2 points seems to give a good fit based on the scatter diagram. And I will show you that here on the next slide here. Let me go over there. Here's the points. We drew a line. So they thought, well, that kind of follows the data. 1, 2, 3. They got 4 above, 1, 2 below. I maybe would have picked this one and this one, because when I draw through there, I see 3 above and 3 below. Again, if you're doing it by hand, everybody's going to pick different pairs of points. So we're all going to be slightly different if we do it by hand. Okay. The first thing you would do is, going back to basic algebra, we would calculate the slope. So that is to take y2 minus y1 over x2 minus x1. So 275 minus 258 over 105 minus 99. So 17 over 3, or 2.8333. That's my slope. Okay. We would then use the point slope formula to find and work backwards to the equation of our line. So again, this is super duper algebra heavy. So we know what y1 is, we know what our slope is, we know what x1 is from back here. x1, y1, and slope. So what they do is they plug into the equation and solve it all the way down to what y equals. And they get this equation. Our goal is always going to be y equals mx plus b, where m represents the slope and b represents the y-intercept. Okay, slope is always attached to the x, and y-intercept is always the value by itself. All right, so we would have already drawn the line, because I would have picked my 2 points and drawn my line through it. So that's what they did here. They picked their 2 points and they drew their line through it. Okay. Once you have your equation, you could then use it to make predictions. So what I could do, as it says, use the equation to predict the distance a golf ball will travel if the club head speed is 104 miles per hour. Well, 104 miles per hour is the x value. So I'm going to put x into my equation. So 2.8333 times 104, and then subtract 22.4967. And this is what my equation is predicting out for you. Okay. I think 104 was one that we didn't do. So it looks like right between 270 and 275 based on my line. But that's between those 2 points. If I had picked different points, it's going to estimate a little higher, maybe a little lower, depending on what I do. clearly doing it by estimating is not going to be the most exact method. Okay, so one thing we can do here is we could talk about the observed value and predicted value. So let's pick one that we did do. Okay, so we know from our data when we plug, so we're going to do 103 for a club speed of 103 miles per hour. All right, so if I go back here, 103 has an actual value according to my study was at 274. So 103, my observed is 274. Okay, my predicted is going to be based off of my equation. So let's say I go back here and I do plug in 103. So 2.8333 times 103 minus 22.44967. I'm just going to grab out a basic calculator and I get 269.33. So the predicted is 269.3. Okay, so what you can calculate here is how far your predicted is from your observed by calculating what is called a residual. For a club head of speed 103 miles per hour, the residual is your observed y minus your predicted y. So you're trying to figure out how far off your equation is. So if I take 274 and I subtract 269.3, I get 4.7 yards. So basically what that means is between these two, what I predicted with my line and what I observed, I have a difference of 4.7 yards. And I'm going to show you that on the next line here. So just this value was my observed, and this is my predicted from the line. And you can see how far apart it is. What we're going to do is our goal is to create the least squares regression line, which is going to be the line that minimizes the sum of the errors or the residuals. So what we're trying to do is we are trying to make this line such that if I add all of these distances here to the line, I get the smallest result. Okay, I want these to be as close to the line as possible, have the least amount of deviation from my line here. And that's too hard to do by just picking 2 points. So our least squares regression line is what we are trying to do is minimizing the sum of our residuals squared. So I would take each residual here and square it, add them all together. And if I can find one smaller, then I move my line a little bit differently. So clearly this is not something we would just do by hand. It is something that technology does very, very quickly for us. There is an equation we can follow here. So again, I'll show you kind of working through how to do this by hand if you want. All right. So we can create the correct least squares regression line. So back here, we just created what we thought to be a good line of fit. Okay, this was just an estimate of a line of fit. When we go to the next part here, we are creating the best. This is the best of the best. The best line of best fit, the least squares regression line. Okay, so if you have your data, we can calculate the slope as follows. Taking your correlation coefficient times by the standard deviations of y divided by the standard deviation of x. And then the y-intercept is the y mean minus the value we just got back here times the mean of the x's. Okay, and I believe all of these were values we had. All right, so what I need, so let's stat, summary stat, columns. I need both of them. So I can click both of them by, it says you select more than one, shift click. So I shift and I click another one and click compute. So I need means and I need their standard deviations. If I'm gonna do this here, and I know it shows me on the next slide how you do it all out here, but I'm gonna work it through with you. Oh shoot, we also need the R value. What's the R value? Go back here. So R 0.939. 0.939. R was 0.939. Standard deviation of X, standard deviation of Y is what I need, right? And then Y mean and X mean. Mean of X, 101,875. Mean of Y, 266.75. Okay, standard deviation of X, 2.295. Standard deviation of Y was 7.741. If I wanted to do this, if I find my slope, I would take 0.939 times 2, nope, standard deviation of Y. Pick the right one. 7.741 divided by 2.295. So the best slope is 3.167. And if we go back here, ours, when we made ours, was 2.833. So clearly our slope was a little off. But again, that's what happens when you make it on your own. Next up, we're going to find the y-intercept. So we take our y mean, 266.75, minus b1, 3.167, times 101.875. Okay, so the next thing that we have to do is calculate our y-intercept. So using our formula, y's mean, 266.75, minus B1 back here, 3.167 times X bar 101.875. So if I go ahead and type that in my calculator, I get an answer of negative 55.88. So using these formulas, the least squares regression line would be 3.167x minus 55.88. So this should match pretty closely to what StatCrunch shows me, and I will double check that here in just a second. But you can definitely see that this is a lot different than the one I estimated and got. Back here, the slope was 2.83 and the y-intercept was negative 22.49. And this slope is in the 3s and the y-intercept is in the negative 50s. So one other thing to note here, I did round a little bit when I wrote all of these values down here. So these may be slightly off from StatCrunch. The less rounding, the better. But do know that this is a lot better of a by hand method than just randomly picking 2 points. So let me go back. Again, it's me a little off because I rounded. I had negative 55.88 and 3.167. So I was pretty close to what StatCrunch did here, but I rounded. StatCrunch didn't round. So just to show you again here, it does have all of the work done for you in the PowerPoint that we did do by hand on the previous slide. So it does show our standard deviation for X and Y, calculating your B1 value, and then on the next slide, going and calculating your BO value and getting the same equation we got on that previous slide. some equations use y and y hat to represent the predicted value. What does it mean? Two options. It is an estimate of the mean value of the response variable for a particular value of the explanatory value. So it's an estimate for what you plug in for x, or it's an estimate for the response for the explanatory. Same thing. It doesn't matter if you're using estimating for your however you're talking about it, you're estimating the response, you're estimating the y given an x. It's just, are you talking about the average value or just a single value? Okay, so how did we do this in the technology? Well, you did it last time. You just didn't know that you did it last time. So it was in these results from before when we went to stat, regression, simple linear. We selected x and we selected y. So what we looked at this first section was just the correlation coefficient here, this guy. If you go up here, here's your equation. Distance is the y value. Here is the slope. Or sorry, no, the second flips it. I'm sorry. Put the y-intercept first and then the slope with the x. If you don't know which is which, you can always look down here. The intercept is the -55. Slope is 3.166. Okay, so if you needed to know, hey, oh, which is which, they're down here. I think back, we plugged in an estimate for 104 and we did an estimate for 103. So let me see what our estimates were back here. So we had, with our original equation back here, our, we did what? 104 with our original estimate gave us 272.2. And when we first estimated 103, we got 269.3. So what happens if we use our new equation? Okay, so we're going to use this new equation here. I showed you how to do that. That's already on there. Predict the mean distance the golf ball will travel when hit for 103 miles per hour. So we're going to see how our test, when we first did it, how it compares here for the 103. So using our most correct formula, 3.1661 times x minus 55.7966, we're going to plug in 103 for x. So 103 goes in here, times that by 3.1661, and then subtract 55.7966. I'm going to get 270.3. Okay, remember that our estimate early on was, what did I say? 69.3. That was our estimate when we drew the line. This is the most accurate method here. Last thing we can do is determine a residual for the predicted value. So for 103, remember the exact was 274. Residual is taking the exact value minus what we got for our estimated according to our equation, which was 270.3. And now our residual is smaller, 3.7. When we did this by hand all the way back here, our residual was 4.7. So clearly, when we use the least squares regression line, this residual is as small as it will possibly be. When we do it by hand, we can't just guess that to happen. We have to use this exact formula here or use the technology to help us. And it's going to then create, if I do any of these, any single pair that I pick, that residual is going to be the smallest. Okay, one thing that we can note here is this residual is positive. That means what we got in our observed, what we actually saw happening was slightly above average for what should happen according to our equation. Our equation is this is what should happen. It should be right at 270.3. What we got was a little higher than that, a little above average. So if our residual was negative, it would be that, hey, the value we got when we tested it is actually a little below what should have happened, or a below average. Let's do another example. Okay, so remembering that once you're in the class here and you click, where's my cursor? There we go. When you click the StatCrunch tab, I'm on the StatCrunch tab, I'm going to go to view data sets from your textbook. We are in chapter 4. We are in section 2. So I'm just going to pick one and hope that it works here. All right, let's do this one. All right, we have length and weight. I don't know what it is that we've measured the height and weight of, or the length and weight of, but we are comparing length and weight. All right, so if we want to create our graph and find our line of best fit, we are going to go to regression, simple linear. Okay, you're going to go X is the first one, Y is the second one. Okay, so again, I showed you how to do it by hand, guys. If you want to try it and you want to double check that it matches here, fine. Please, it's so much faster though to just use StatCrunch here. I just did this in a matter of a few clicks. All right, it's so much faster. It's so less frustrating than if I was to use a calculator and by hand. All right, so if I go here, I can look at my R value. So R is 0.7039. So it's positive. Look at the graph. Does it look? See, there's some decent separation there. So I'm going to say moderate. I don't think that's super strong. I'm going to say moderate positive. Okay, third line down is the equation. So y equals negative 142.47 plus 1.69 times your length, so 1.69x. One that we have is, I'm going to pick one that we only have one of, 139. All right, so let's estimate x equals 139. All right, we're going to plug it in. Y equals negative 142.47 plus 1.69 times 139. Oops. 139. I don't know how I got those extra values in there. Okay, so take a calculator, negative 142.47 plus 1.69 times 139. All right, I got 92.44. So according to my formula, according to average, on average, if you are 139 centimeters, your weight should be 92.44 kilograms. I observed, if I can click here, for 139 I was 110 kilograms. All right, so this person is above the average value. They should be around 92 centimeters, 92.4 kilograms. They're 110. Okay, they're above what we would expect. Let me see if I can find one that would be. Okay, so let's do another one here. Let's do 149. Estimate at 149. So y equals negative 142.47 plus 1.69 times 149. Let's see what we get. All right, get 109.34. Okay, so if the object is 149 centimeters, it should weigh about 109.34 kilograms. 149 centimeters should be on average 109.34 kilograms. Okay, ours at 149 was 85. Okay, this one is below average. Okay, so what we observed here was below average. And you can see how far apart these are. 92.4 to 110, that's a big difference. 109.34 to 85, those are big differences. That is why my correlation coefficient is not in the 0.9s. That is why. You can see how far apart these points are. So the further away the points are, the less your correlation coefficient is, the less the strength of your relationship. Yes, there's still a relationship, but when those values are so far apart, they're not as strong. I hope that makes sense. I'm working through a whole example there. The last thing we can do is explain or interpret our slope and interpret the y-intercept. From algebra, we know that slope is rise over run, or the change in y over change in x. So if we had a slope of 2/3, what that means is this is the y, this is the x. So if x increases by 3, y would increase by 2. So for every 3 increases by x, y goes up by 2. All right. If the slope was -4, the fraction would be -4/1. So when x goes up by 1, y goes down or decreases by 4. Okay, when we create these linear models, these linear regression lines, everything's going to be based on like this. X is increasing by 1. How is y going to change? Any predictions and the interpretations that we make are all based on a little bit of uncertainty because we've just taken a sample. So anything we state here is always going to be, just remember that we are never 100% certain with these results, because if I ran the test again, I could get different results and then my line could change. So samples can never be 100% certain, but just so you know. How do we do this? So going and looking at the equation for the club, going back here, where is it? Here's the slope, 3.1661. So here's how they do it. If club head speed increases by 1 mile per hour, the distance the golf ball travel increases by 3.166 yards on average. Okay, another way to say that, if the club head speed increases by 1 mile per hour, the expected distance of golf ball will travel increases by 3.1661 yards. What I'm going to do is I'm going to try to make this a little bit easier for you. So for each additional, fill in the blank what happens with x. So for each additional, well, x was mile per hour. So for each additional mile per hour in speed, what happens? The y, which is distance, so you're filling in y, what it is, and then you're going to tell me, is it increasing or decreasing? So you have a choice, increases or decreases. In this case, it's increasing because our slope is positive, by fill in your slope. My slope is 3.1661 and whatever the units are, yards. Anytime I talk about slope or define slope, this is how I'm going to do it. For each additional fill in the blank that I'm talking about x, the y, whatever it is, does it increase or decrease, and by how much? I could go back and I can look at any other example here. So let's go back and look at this guy that we did here. Where is my cursor? For each additional x, so x is centimeter in length, L-E-N-G-T-H, the weight, And what was our slope? Slope increases. So the weight increases by 1.69 kilograms. That is how I will always write it. For each additional, what is the X? The Y increases or decreases by whatever your slope value is. Okay, for me, that makes more sense. I could look up, let's see, we have another one here. That was, I don't know if I have another one. We had credit score and interest rate. So let me go here. Slope was negative. Okay, so let's see if I want to do this. So slope for each additional point, in credit score, the interest rate in this case goes down, decreases by, what was the value? 0.076, and I'm assuming that's a percent value. If it's a negative value for slope, you say decreases, positive increases. So that's how we define slope, or interpret slope. Again, I do it with lots of examples to try to help you guys out here. Okay, y-intercept is a little different here. So first off, the definition of a y-intercept is the point where the graph intersects the vertical axis. Okay, it is the y value when x equals 0. However, some situations do not let us really interpret this. So what we're going to do is we're going to look at our data set. Okay, do we have any, So I'll look at two first, Do we have any observations that are near 0? When we look at our data set, are any of our x's close to 0? Because if they aren't, it's probably not worth discussing. Okay, second question we can ask ourselves, or in this case, the first one, is 0 a reasonable value to plug in? Can I plug in 0? Does it make sense to plug in 0? If we answer no to either of these questions, we can't do it. So when we work with this swinging of a golf club, does it make any sense to swing a golf club with no speed? No, it makes no sense. I would never do that. So there's no no x values that are close to 0. It makes no sense for me to discuss the y-intercept there. So looking here at credit score, do I have any x values close to 0? No, there's no y-intercept. The y-intercept makes no sense. Club speed. It makes no sense. There are no x values close to 0. The y-intercept is not something that we would discuss. Let me see, what else do I have here? Okay, length and weight. This one is another one that would make no sense to have anything discussed. All right, let's do this one. All right, so we got our annual return on investments and our cost. So let's graph that one. Stat, regression, linear with your ROI to your cost. I've got lots of values here. If you look at it, I have really close to 0 going up to 10. So it looks like in this case, I could have 0 as a value. It does make decent sense here because I have some values like 0.6, 0.8. So it's definitely something that I could get really close to here. Anytime you're talking about the y-intercept, it is the y value when x is 0. So just to do both, we can do both here. We can talk about slope and y-intercept. Let's talk about slope here. So the slope for each additional point in ROI, the cost, oopsies, the cost, let's see, our slope goes down, decreases by, and this is going to be money, so $8,051.12. For a y-intercept, we would say when ROI is 0, the cost, oopsies, whatever that y-intercept value is. So this guy here, 18,000. No, what is that? That's an 18,000. $181,503.95. The better your ROI, the lower the cost. Okay, so anytime you want to discuss y-intercept here, it's going to be whatever when x is 0, so whatever the x's you're talking about is 0, what value your y is going to represent. Okay, so again here saying for this one, we couldn't use it. We don't know if that's going to continue. We don't know how it's going to continue. So we don't know what happens outside of that scope of our model. All right, so that is the end of section 4.2. I'll see you back here in section 4.3.